Hello my esteemed viewers. In this tutorial, we clearly present how temperature variation can bring in stresses in the components, and these stresses are coming to be called as thermal stresses, and they are also called as temperature stresses. Temperature always brings about changes in the objects. This is well known to us. When they expand when temperature is increased and contract when they are cooled. And here is an example. There is a cube and it is being uniformly heated, let us say, and it has the initial volume V naught. Upon uniformly heating and upon providing for a free expansion in all the directions, the volume of this component is going to increase. And on the other hand, if it is cooled uniformly, it's going to contract and come back to its original volume or original shape. And nothing will happen when objects are allowed to expand or contract freely in all directions. It's like this. Water will also expand, and when it is heated beyond 4 degrees centigrade, and when it is cooled beyond 4 degrees centigrade. When materials expands or contracts freely due to temperature variation, it is said to undergo thermal strain. So here is a special case where thermal strain happens first, and prevented thermal strain. If we prevent this thermal strain by some means, thermal stresses is going to crop up. So strain is the cause and stress is the effect. Unlike the discussions that we held earlier, where stress was the cause and strain was the effect. The uniform thermal strain is given by epsilon t equal to alpha into delta t. And we know epsilon t, that is strain, is change in length by original length, that is equated to alpha into delta t, where alpha is the coefficient of thermal expansion, purely a material property, and dl upon cross multiplying we get alpha into delta t into L. The coefficient of linear thermal expansion is a material property that is indicative of the extent to which a material expands upon heating. Different substances expand by different amounts. So this is a pointer for us to understand. Higher the coefficient of thermal expansion, high is the amount of magnitude of expansion or contraction done within the material or observed over the material, and low is the value, low will be the expansion and contraction. And this thermal coefficient can be measured by various methods. Among them, the predominant methods are dilatometry, interferometry, and thermomechanical analysis. Anyway, we are not going to concentrate our discussion on how exactly this thermal coefficient of thermal expansion is measured, but however, we definitely emphasize that this is the material property, and the thermal expansion of material and contraction due to cooling is dependent upon this particular property, and it is expressed as so many millimeters per degree rise in temperature. The coefficient of thermal expansion is also often defined as a fractional increase in the length per unit rise in temperature. Problem arises when free expansion and contraction is prevented, and this is the point. This is the gist of our discussion. Whenever the free expansion and contraction due to temperature variation is prevented, it's going to crop up thermal stresses within the material. And when a concrete slab is prevented from free expansion, it's going to buckle like this, leading to some kind of a crack. And if a specimen is tightly fitted between unyielding walls, and when it is cooled, it's going to contract and tension forces will develop. So prevented contraction will lead to tension, and prevented expansion will lead to compression. And we know the reason why the expansion gaps are provided in case of rails. If it were to be not provided due to excessive expansion, the rails will buckle, leading to derailment. If free expansion is prevented, compressive stresses sets in the component. This is thermal stress. On the other hand, if free contraction is prevented, during cooling, tensile stresses will set in the component. This is also thermal stress. Therefore, thermal stresses will develop over here, contrary to our expectations, by prevented strains, and this strain will happen naturally due to thermal changes or changes in the temperature. Concrete slabs will develop cracks if thermal contraction is prevented, something like this. This is thermal crack. It is very easy to identify whether a crack that is formed in the concrete is thermal or not. If a heated metal is not allowed to contract freely, tension will develop, as we said earlier. Therefore, we used stresses of varying nature, of varying degrees, in order to cause strains. So we drew a diagram also explaining as to how mild steel will behave for the increasing stress versus strain diagram. Here strain comes first, and if this strain is allowed to happen freely, nothing will happen. Of course, the prevented strain will generate what is called as thermal stress in the material. Thermal stress may be defined as the stress required to produce the prevented expansion or contraction. So this is the nature of the stress that we are going to define, and it is in the definition itself. So thermal stresses may be defined as the stress required to produce the prevented expansion or contraction. So here is a member which is being prevented by the unyielding walls for the contraction, free contraction. Automatically it will go stretched, and the contraction will lead the material to go in the backward direction. But anyway, the unyielding walls will never allow it to happen. Therefore, this gives rise to tension. And for certain materials like concrete, the thermal strain is not linearly related to the temperature. We cannot write alpha delta T into L. Okay, and it varies non-linearly. The changes in the stress values. Another unusual changes in the strain values, of course. Another unusual material is water, which expands when heated above 4 degrees centigrade, but also expands when cooled below 4 degrees centigrade. Hence, the density of water is referred at 4 degrees centigrade. But we restrict our study with materials which show linear relationship between thermal strain and temperature. Thermal stress. We will develop an expression for thermal stress starting from the known things. We start from epsilon T is given by alpha into delta T. This is thermal strain. Alpha into delta T. Therefore, thermal strain is directly proportional to coefficient of thermal expansion and change in temperature. Therefore, delta L comes from the fact that epsilon T is delta L by original length, because this is also a definition of the strain, and in the definition of the strain we told delta L by change in length by original length, and when we write this, when we cross multiply, we will get change in length owing to temperature is alpha into delta T into original length. Now, delta length is also given by, change in length is also given by PL by AE. Here it is PT, it is thermal force. PT into L divided by AE. And we will remove this PT by A only to get the thermal stress. Delta L equal to thermal stress into L divided by E. Therefore, and dl, we have this particular expression. We will resubstitute alpha delta T into L equal to sigma T L divided by E, and upon simplification L and L will get cancelled, and we will get sigma T, that is thermal stress, equal to coefficient of thermal expansion into change in temperature into elastic modulus, and this is epsilon T into E. Okay, because alpha into delta T is nothing but the thermal strain. Therefore, it reduces to our famous Hooke's law, and Hooke's law is also still applicable wherever stress is related to strain, or stress happens due to strain or vice versa, but within the elastic limits. And here it is a special case where thermal stress and thermal strain are related. It is prevented. We should hasten to add that it is prevented thermal strain. Okay, we will understand the concept with few illustrative examples. First example is a copper bar AB of length 1 meter is placed in position at room temperature with a gap of 0.1 millimeter. A gap is provided, assuming that this would suffice. Okay, it's an expansion joint. Let us say a gap is provided. Let us see as to what will happen. End B and rigid wall. So this is the gap between the rigid wall, and anyway this rigid wall is not going to yield. It's not going to move further if this expands. Therefore, if the amount of expansion is more than 0.1 millimeter, 0.1 millimeter exactly, it's wrong, it's not meter, millimeter, definitely thermal stresses, thermal compressive stresses ought to develop. Therefore, we will continue. We first calculate the change in length or elongation of the bar due to increase in temperature, assuming that it is allowed to freely expand. So delta L is alpha delta T into L, and we will substitute the values. This is for alpha, this is for delta T, change in temperature, because it rises above the room temperature. Therefore, this is the change in temperature into 1000. That will give us 0.68 millimeter. But anyway, we have provided only, the allowance is made only for 0.1 millimeter. Therefore, 0.58 millimeter is restricted. This amount of expansion is restricted, which will become the reason for the development of the thermal stress, and it will be compressive stress. But the bar can expand freely only for 0.1 millimeter. Therefore, the prevented elongation is 0.68 minus 0.1, 0.58 millimeter. The thermal stress that is needed to produce the prevented expansion of 0.58 millimeter is given by delta L equal to sigma T into L by E, and in place of delta L we will place sigma T is therefore equal to, with a small adjustment, tweaking of this particular formula, and sigma T we will substitute the values over here. E is 110 into 10 to the power of 3 MPa, 0.58 is the change in length owing to prevented expansion, and the original length was 1000 millimeter. Therefore, it will get us 63.8 MPa. That means this means simply this: there is a thermal stress of amounting to 63.8 MPa is developed due to prevented expansion, or this is the force that is, this is the stress that is required in order to cause this, right? As the expansion is prevented, the bar is subjected to compressive stress. A steel rod of diameter 20 mm and length 5 meter is held tightly between the walls without any initial stresses as shown. Calculate the drop in temperature at which average shear stress in the 15 mm diameter bolt becomes 60 MPa, and take alpha equal to this much and E equal to this much. And here is an arrangement. There is a bar with a end, something like this. This end is fastened with a bolt, and this bolt is tightly tied to this particular wall, and walls are unyielding. Therefore, the temperature is cooling. The temperature is being cooled, and when the cooling happens, to a particular degree temperature, it will cause tension in this bar because a contraction is prevented. As far as the force in this bar is concerned, it is a tensile force, and this tensile force will create the shear here, and the shear here is a typical example of a double shear, because if it breaks, it will be into three pieces, one here, one at this interface, other at the interface. Therefore, two areas of cross section is participating in taking the shear, and the shear has been measured to be 60 MPa when the temperature was cooled. And we have been asked to find out the thermal stress, temperature, okay, change in temperature when the average shear stress in this bolt becomes 60 MPa. Therefore, we will start. When the temperature is brought down, the steel rod will be under tension, the bolt will be in double shear. The force causing the shear in the bolt is the tension in the rod, which is held tightly, preventing the free contraction. So we will start from the known values. Average shear stress is given to us, but anyway, as far as bolt is concerned, it is subjected to double shear. Therefore, it is P by 2A. And 60 is given. This is the average shear stress at the time of cooling. So P into 4, that is 2 pi into 15 square, because the diameter of that particular bolt is 15 millimeter. Therefore, it is double shear, 2 times the area. Two areas of cross section participates. This has been well explained in our previous tutorials. Therefore, 2 pi into 15 square divided by 4 will go up, and we will get a value of the force that is in the rod equal to 21,205.75 Newton. And this is the cause for the double shear in the bolt, and this will create tension in the rod. Consider the rod. The thermal stress in the rod is sigma T is equal to E into epsilon T, and thermal stress, because we know the force over here, force divided by area. The rod diameter is 20 millimeter, therefore pi into 20 square divided by 4 will go up, and this is the force. This is equal to E 200 into 10 to the power of 3 into 12. Epsilon T is written as delta T into alpha into delta T. Alpha is given and delta T we have to compute. Therefore delta T becomes 28.12 degree. So it is to be cooled by 28.12 degree, okay, from the earlier temperature. Then only the average shear stress in the stud or in the bolt will be 60 MPa. Right. Steel rails were laid during winter season when average temperature used to be 5 degrees centigrade with 3 millimeter gap at the ends of each rail. So gap provided for the free expansion is just 3 millimeter. The rails were 10 meter long. This will give us the initial length or the original length. During summer, the temperature rose to 45 degree. So temperature rises to 45 degree. Therefore, change in temperature is 45 minus 5, 40 degrees centigrade. Determine the thermal stresses developed. Given alpha equal to this much and E equal to this much. Now, length of the rail equal to 10 meter. Rise in temperature is 45 minus 5, 40 degree. Therefore, the free expansion of the rail is dl equal to alpha delta T into L. And we have derived this 12 into 10 to the power of minus 6 into 40 into 10,000. So 10 meter is converted into millimeter. That will give us 4.8 millimeter. But we have left only, the allowance is made only for 3 millimeter. Therefore 1.8 millimeter is prevented. Therefore the thermal stress is equal to the value of the stress which is required to cause the prevented change in length. That is, prevented change in length is 1.8 millimeter. That's how we calculate. So free expansion prevented is 4.8 minus 3, 1.8 millimeter. Therefore the prevented strain is 1 point change in length 1.8 millimeter by the original length. It will give us the prevented strain, that is equal to 1.8 into 10 to the power of minus 4. Therefore the thermal stress is given by thermal stress equal to E into epsilon T. E is this one given, and this is the prevented strain, which will give us a stress of 36 Newton per millimeter square. Therefore the rails will be subjected to 36 Newton per millimeter square, which is compressive in nature. An aluminium rod 2 meter long is secured between two walls. This is the rod. It is secured between the two walls. Compute and the stresses in the rod was 0 when the temperature was 10 degrees centigrade. Compute the stresses when the temperature drops to minus 10. So temperature changes from 10 degree positive to minus 10 degree. Therefore change in temperature is 10 plus 10, that is 20 degree. So given alpha equal to 23 into 10 to the power of 6 minus 6 per degree rise in centigrade and E equal to 60 GPa. Solve for two cases, assuming 1 that the walls are rigid, 2 that the walls yield by 0.5 millimeter together as temperature drops. So case first is the expansion is contraction is prevented, and case 2 some allowance is made in terms of yielding of the walls. Therefore no yielding of the walls. If the case is 1, the first case where the walls are not yielding, full thermal stresses will be developed, which is tensile in nature. And here this is the thermal stress, thermal strain that is going to happen, but anyway it is being allowed to expand, to contract by yielding of the wall. That is, wall will also move in this particular direction to an extent of 0.5 millimeter, and this is contraction due to temperature strain. Therefore this the difference between this and this will be the prevented contraction. We will just say this: when the walls doesn't yield, if the rod were to be disconnected from the right wall, it would have freely contracted to the full extent. However, this is not possible as the walls are unyielding. Therefore we will apply this formula: change in length equal to PL by AE, and change in length exclusively due to temperature is alpha delta T into L, sigma T into L by E, and we will delta T is plus 10 degree to minus 10 degree. Therefore it becomes 20 degree. Change in temperature is 20 degree. Okay, alpha T sigma T equal to epsilon E into alpha into delta T, and we will substitute the values. this is value of E, and this is value of alpha, this is value of delta. We will get sigma t equal to 27.6 MPa. And in the second case, naturally you must have guessed, the stress value must reduce because some kind of an allowance is given for the free expansion to the tune of 0.5 millimeter. When walls yield to an extent of 0.5 millimeter, when the walls yield together, free contraction is facilitated to some extent by yielding walls. The free contraction is equal to the deformation caused due to the thermal strain minus, it should be minus, amount of the yield of walls. Deformation due to temperature equal to change in length due to thermal effect minus extent of yield of walls. We will substitute this. We know the deformation, that is change in length, is sigma t divided into L divided by E. It comes from PL by AE. Of course, we have thermal stress over here. Our change in length due to thermal effect, this is alpha delta T into L minus yield of the wall. And we will substitute this. Sigma T 2000, length is 2 meters, therefore it becomes 2000 millimeter. E is 60 into 10 to the power of 3 equal to 23 into 10 to the power of minus 6. The value of alpha. Delta T is 20 and the length is 2 meters, therefore 2000 millimeters minus 0.5. It will give us sigma t equal to 12.6. So this compares with the previous value, which happened to be 27 point something, and almost half the value has been reduced because we have made a provision for the free contraction to an extent of 0.5 millimeter. The fifth problem happens to be like this. A steel wire AB is stretched between rigid supports as shown. The initial it could be a rod. We will say it as a rod. Okay, we'll make a small change over here. We will just read this as a rod. Okay. A steel rod AB is stretched between rigid supports as shown. The initial stress in the rod is 30 MPa. The initial stress in the rod is 30 MPa. This is pre-stressed. A rod is pre-stressed at a particular temperature which is 20 degrees centigrade. Okay, which is 20 degree centigrade. Now the question goes like this. What is the stress in the rod when temperature drops to 0 degrees centigrade? So the stress must increase beyond 30 MPa because we are cooling, but the contraction is provided. Contraction is not allowed. The free contraction is not allowed. The second question is, at what temperature T will the stress in the rod become 0? So in order to make the stress in the rod to be 0, we need to heat it till the stress happens to be compressive stress amounting to 30 MPa. So here is a pre-stress of negative, that is a tensile stress of 30 MPa, and we are going to heat it further in order to make the stress condition to be 0. Therefore 30 and 30 will cancel away. The compressive stress will nullify the pre-stress of 30 MPa. So we will solve this problem with this idea. The temperature at which wire is pre-stressed was 20 degrees centigrade. Therefore the wire is to be cooled to bring the temperature to 0 degrees centigrade. The wire will be in tension because the free contraction is prevented. Sigma t is equal to epsilon t into E. Epsilon t is alpha delta t into E, and we will substitute the values, given values. Alpha is 14 into 10 to the power of minus 6, and change in temperature is 20 degree, and E is 210 into 10 to the power of 3, which gives us 58.8. Due to cooling, there is an increase in the value of the tensile stress, 58.8. We need to add the pre-stress to state the stress condition when the temperature is reduced to 0 degrees centigrade. So magnitude of stress in the wire is 30, the pre-stress, plus 58.8. So it becomes 88.8 MPa when the temperature is brought down to 0 degrees centigrade, but the contraction is not allowed because it is being held tightly between the supports. In order that the stress in the wire be 0, the temperature should increase such that the thermal stress in the rod will become compressive in nature with a magnitude of 30 MPa. So here we have the stress value which is compressive in nature, so we will calculate the temperature, increase in temperature beyond 20 degrees centigrade. So sigma T is equal to epsilon T into E, and we will have this formula, expanded formula. So 30, this is the known stress is known to us, this should be of compressive nature, and epsilon T is 14 into 10 to the power of minus 6, and delta T 210 into 10 to the power of 3. We will substitute for this portion of the formula, and we will get delta T equal to 10.2 degree centigrade, and it is to be heated beyond existing 20 degree centigrade, where the temperature happens to be the stress happens to be 30 MPa in tension. Okay. Now temperature should be 20 degree plus 10.2 degree, 30.2 degree. Then only the stress, the rod will reach a zero stress level. So with this we will notice a very important observation. We are going to make a very important observation. I think you must have guessed. Poisson's effect and thermal effect have one thing in common. In Poisson's effect, the lateral contraction of a bar or a rod in tension, or lateral bulging of a cylinder in compression, is an illustration of strain without corresponding stress. We never pull sideways, or we never push sideways. When a rod is extended or elongated by means of a tensile stress, its sides is going to decrease. Its sides will become lean, will become thin, and we have never applied force in that particular direction or stress in that particular direction. Likewise, thermal strain occurs without stresses, and this strain is produced due to change in temperature. When this strain is prevented, it is going to become a cause for the development of thermal stress. With this tutorial, we come to the end of the concepts of simple stress, simple strain, and we know that simple stress can be broken into two broad types: the normal stress and the shear stress. And the normal stress, there are two categories: compressive stress, tensile stress, and shear stress is the other category. And we have understood the corresponding strains, and there it was stress was the cause and strain was the effect. And in this thermal stresses or thermal strains, the prevented strain will become a cause for the development of the thermal stress. So we will come to an end, and in the next tutorial sessions we will tackle, and we will demonstrate how exactly, if the component is loaded laterally, what happens to the component, and the indirect stresses, the cropping up of indirect stresses, and bending, shearing, everything we are going to refer, or we are going to deal at length as far as beams are concerned. So next point of discussion is regarding the beam and beam action. Until then, bye, and if you have liked this video, kindly subscribe to my channel. Thank you.